All right. Thanks for coming. Very happy to introduce Subhadip Singha, who is a postdoc here in our department, working with Douglas. Subhadip did a master's and PhD at the Indian Statistical Institute, and has come here after that, and will tell us about lab production. Thank you.
Hello. Thanks, Sam, for the introduction. My work that will be presenting here in complex security analysis of lattice-based reductions. And yeah, now it's working.
Okay.
So the work is this is a joint work, Professor Paul Shorter, Professor Neil Kopis, and Dr. Shobhut Samatha, and there is a different link of the paper, actual paper. So I'll be talking about cryptography. So cryptography in a nutshell is the art of secret communication and between two users or more users. And historically, we've seen that symmetrical cryptography is the one which came first, where the users have same. The users will share some secret key, and then the public key cryptography came, where so we have the relaxation that we need not to have same secret key. Instead, we have two keys. One is public key, and other is private key. Public key is public to all, whereas private key is private to the user. Somebody wants to send me data, so they'll use my public key to encrypt the data and send it to me. So the current public key cryptography consists of RSA and Diffie-Hellman. And where the symmetric key, current symmetric key cryptography, we can say AES and BS are the market leaders. So one thing which is common to both of the two types of cryptography is provable security, the security of a crypto system which can be proven. Because the initial part of cryptography back in like 200 years back, we had cryptographic schemes, but we didn't have any proof to prove them that they are secure. For example, RSA is based on prime factorization, Diffie-Hellman is based on discrete logarithm problem. And these proofs are reductionist proof because the security of crypto system is reduced to some underlying hard problems. So the proof goes like, if I can solve a cryptographic system based on Diffie-Hellman, I can solve the discrete logarithm problem. Okay. So this is I can say the basics of cryptography that we are using for last few decades. And there are two more notions of security. One is perfect security, and another is computational security. So in perfect security, we say that a crypto system is perfectly secure if no adversary can break it regardless the power, computational power it has. So it can have infinite computational power, but it cannot break the crypto system. And a well-known example of that is one-time path. But on the other hand, computational security, the power of the adversary is not infinite, or it is bounded by polynomial time algorithm. Like we can say that the adversary, we can model adversary as PPT, probabilistic polynomial time algorithm. And modern crypto system like RSA and AES, this offers computational security. So if I have an arbitrary adversary which has like huge exponential power for time and memory, they can easily break RSA and AES or Diffie-Hellman based crypto system. But the current adversaries, which are like practical adversaries, they cannot break it. The computational secure systems. So this is we call these cryptographic system as a classical one, because when we are talking about adversaries, we are talking about classical adversaries. But in 1997, Peter Shor came up with one quantum algorithm, very what can you say, like simple quantum algorithm for integer factorization and discrete logarithm problem. So the public key cryptography, which is based on Diffie-Hellman and RSA, can be broken using Shor's algorithm. But Shor's algorithm requires a huge quantum computer, which is still not a reality. So the current crypto system that are built based on RSA and Diffie-Hellman are still secure. But from that time onwards, we started to find cryptographic scheme which are secure even in, with the quantum attacks. And the prominent classical candidates which are resistant to quantum attacks are like lattice-based, code-based, isogeny, multivariate, and hash-based. And among these five are well known. Few of them people have come up with schemes and were broken, not with the help of quantum attacks, but with the help of normal classical computers. So the state is right now we can say that we have some theoretical background, but practically we don't have something in our hand. And other than this classical candidates, we have a big ocean of quantum cryptography, which is a still open area for research. So first quantum secure classical candidate was proposed in lattice based in 1996 by Altai and Dock. And for next 20 years, we have lots of research over that. And in 2017, the National Institute of Standards and Technology (NIST) of the USA called for proposal for post-quantum crypto system, because right now we are using RSA and Diffie-Hellman. So right now all those encrypted data can be stored, and when the quantum computer is available in reality, can be used to decrypt those data. So that is why these NIST computation was necessary. And the brief history is that this in December 2017, 69 proposals met the minimum criteria to be accepted to round one. And after 3 rounds, evaluation narrowed down to the submission. And in July 2022, NIST announced 4 algorithms to be standardized. One is two are from crystal suits. One is Kyber, another is dilithium, and other 2 is Falcon and Sphinx. Crystal Kyber and crystal dilithium are lattice based, whereas Falcon is also lattice based, but a specific type of lattice called NTRU, and what is Sphinx path is hash based. Few months back in 2024, NIST finally released the specifications of all these 4 and named the first 2 as MLKM and MLDES. KM means key encapsulation mechanism, whereas DES is digital signatures. And ML is short form for module lattices. Okay, so to understand, so our focus is, among these 4 schemes, 3 are lattice based. So one thing is quite like one can understand that lattice is important and necessary to understand, because 75% of them are lattice based. So we'll start with few basic definitions to go into the actual thing. So to define lattice, we need n linearly independent vectors b1 up to bn, which is in Rm. R is the real, and these column vectors and the lattice generated by them is the integer combination of those column vectors. And obviously n is less than n equal to m, and if n is equal to m, then lattice is said to be full rank. And this set b1 up to bn is called the basis of the lattice, or the lattice generated by the basis, or LB. So L is B times Z. Z is my all the Z combinations, so integer combination. So for good examples of some basic examples of lattice are Zn, 2Zn, and anything, any constant power of Zn or any power or any multiple of Zn. So, so these are the lattice examples. First one is the basis of Z2, another one, second one is also another basis of Z2. So both of the bases generate the lattice Z2. So one distinct thing to notice that both bases are not similar to each other. So basis is not something unique. One basis can be found from another basis. So one basis, from one basis to another basis, we need to, if we want to go from one basis to another basis, we need to multiply it by unimodular matrices. Unimodular matrices are matrices of integer values with deterministic determinant 1. And the third one is not a basis of Z2, and fourth one is not a full rank lattice. So another two important properties are this lambda1 and lambda2, the length of the shortest lattice vector, and lambda is the length of nth shortest lattice vector, vector of the lattice. Okay, so as you can see that L1 and lambda1, lambda2 up to Ln can be found, and all so this should be increasing of order in with respect to the length. And another definition, fundamental parallelepiped. So if you go to the next slide, we'll understand this thing. So the first basis is Z2. So the you will point this around is a fundamental parallelepiped, and this is also a basis for Z2, and this is the fundamental parallelepiped for this basis. So basis lattice can be represented by many bases, and the fundamental parallelepiped, the area is also unique, but the shape of this area are different. And these are all examples of fundamental parallelepiped. So with these two definitions, we can go to the hard problem that we find in lattices. The first problem is that shortest vector problem. The shortest vector problem tells us that finding the shortest vector of a given lattice. So to give a lattice, we need to provide a basis B and find out a non-zero vector x such that the length of x is less than every other non-zero vector of the lattice. And the shortest independent vector problem says that we need to find n short independent lattice vectors given a basis for the lattice L, and all are obviously non-zero and independent vectors, and the maximum of these vectors from x1 up to xn, the length of the maximum is less than lambda n of L. And this is a matrix with dimension n and rank n. So we can from a group of like vectors, maximum we can find n linearly independent vectors. And one thing to so these two problems are NP-hard problems. These Harsh-Verson problems are NP-hard problems. And to be specific, these are not NP-complete problems. So if I'm given a solution, I cannot check whether we don't have ways to check whether this is the shortest vector or this is the independent vectors. So the approximate version of SVP and SVP are the following. Given a basis B of a lattice, find a non-zero vector x such that the length of x is gamma times lambda 1 L, where gamma is greater than 1. Obviously, gamma equal to 1 becomes the search version, and same goes for SIVP, where gamma is greater than 1, and the maximum of these n vectors is upper bounded by gamma into lambda n. So for our analysis, these two problems, these variants, and we don't need two more problems. Another is discrete Gaussian sampling problem. So we need to define discrete Gaussian distribution over lattices. So lattices are discrete objects. So all the points are distant by a finite amount of length. So output a vector from a lattice according to a Gaussian distribution over lattices. And another problem is the closest vector problem. Given a point over the lattice pad, we need to find out the closest lattice vector. And the bounded distance decoding problem is a specialized CVP where the distance, so we are given a point on in the whole space. We need to find the lattice point which is nearest to that point, and the distance between the nearest lattice point is upper bounded by some value. So in that case, distance decoding, bounded distance decoding is a specialized version of CVP. Okay. So this was a brief introduction for lattices. So we need another problem, that is LWE, learning with error. So this problem was introduced by Oded Breger. So learning with error is basically solving linear equations where there is some error introduced to it. So S is from ZNP, which is unknown. We need to find S, and AIs are from uniform distribution over ZNP. So we do this inner product and we add some error vector EI. So obviously, so EI is from ZP, because when you do the inner product, we get a value over ZP because everything is under modulus P. Then we add this EI. And if this EI is 0, then this problem can be solved by Gaussian elimination method, polynomial time algorithm we have. But when we add this error, this problem becomes extremely hard. How hard? So if these EIs are uniformly distributed over ZNP, so we cannot solve this problem. So we need to take these errors very close to 0. So we call minus B to plus B. So, and B is very less than P. And a user is given these AIs in form of a matrix, capital A, which contains A1, A2, up to N, and these BIs, and we need to find this S. And that is the problem, learning error. And this is the distribution, like set of AIs and set of BIs are the LW distribution. So this is the short version of LW, and there is another version of LW which is called decision version of LW. So in decision version of LW, we are given similar type of samples. So similar type of samples means BIs and AIs. We know that AIs are already uniform, so we don't have any problem with AI. But BIs are from this LW. So BI means inner product plus error. So if I give the user BIs from uniform distribution and ask whether they are from LW distribution or from uniform distribution, this problem becomes decision LW. So it is conjectured that decision LW problem is also hard as search LW. So this is a toy example. So ZNP and Z47. So these blues are basically A's. So this is a matrix A, and this is the S unknown, and this is the error. Error is hidden. So we need to find A, 8, 3, 12, 5. This is the S vector from this A vector and this B vector. And this is the structure of LW. Okay. So I think I missed one slide. Okay, so I need to go back and show one thing before. So we talked about this closest vector problem, right? The closest vector problem, this is R square. In this R square, this lattice is Z2. So if I give any point within this area, shaded area, so using these two bases, we can do this Gaussian elimination and find that we'll find the coefficients of S as some fraction between 0 and 1. We can round it up to 0 or 1 and find any of the points from these parallelepiped. We can do the same here, but the problem is that here these lattice bases are perpendicular to each other and the length are also small. But here, these bases are not perpendicular to each other. So it can happen that I give you one point here, which is in that shaded area, but very close to this other point, this line. So which is actually close to this x point, but through our Gaussian elimination method or basis reduction, it will show that it is closer to one of these 4 points. So a problem can become hard based on these basis. So one problem could be like I give you one point in R square and ask you what is the closest point, and you give you one random basis, not this one. So when I give you this basis, it is very easy to find which is the closest lattice point. But if I give you this kind of basis, it is not easy. So basically, this is the trick to make the problem hard. So when I'm giving the basis, I'm giving you a random. When I'm giving you the problem and trying to find out what is the closest point, I'm giving you a random basis which doesn't look good, whereas this one is called good basis. So from this geometry, we can understand that a lattice can have infinite number of bases, and from the infinite number of bases, very few bases are of the form this one, like they are either perpendicular or very close to perpendicular. So if the adversary or the person who is trying to solve the problem doesn't know a good basis, it will be hard for that person to find out what is the closest lattice vector. So that is the significance for this LW problem and lattice problems. So I talked about 2 problems. One is learning with error problem, another is problems related to lattices. So how do these problems are connected? They are connected to this paper, Rege's paper on lattices learning and errors with errors, random linear codes. So where Rege showed that the divisional LW is at least as hard as an approximate version of SIVP. So we know that SIVP problem is NPR, some approximation with some small approximate factor, SIVP is still NPR, and this is as hard as this LW problem is as hard as SIVP. So this is the basis for the nowadays lattice-based cryptography. But the main crypto system are based on these papers by Lubusevsky, Picard, and Rege, where the hardness of ring LW is based on the hardness of approximation ideal segment. So I know that what is DLW, this divisional version of LW, and what is SIVP, but I don't know what is ring LW and ideal SIVP. I know. So the ring is an algebraic variant of this division LW, and the ideal SIVP is an structured lattice. So this result is highly influenced by Rege's original work. So the original work was on general lattices or Euclidean lattices, but this one is on ideal lattices. So our analysis is on this paper because the current crypto systems which are considered for standardization are based on these results. So what are ring LW and ideal lattice? So ring LW is an algebraic variant of LW given an algebraic number field of degree n with ring of integers R. So these things are related to algebraic number theory, and ring LW distribution is basically multiplication of 2 elements A and S divided by Q. Q is the modulus. A and S are from A is from R. R is the ring of integer, and S is from dual ideal of R, and E is also dual ideal of R. So this looks messy, But if you simply put that K is isomorphic to R to the power n, where R is real numbers, and through embedding, and if these R is a ring of integers, is isomorphic to Z to the power n, then this becomes quite relatable to actual definition of lattices and LW. And K is a standard embedding into n-dimensional equilibrium space. And the decision version of LW or ring LW is also to distinguish RLW samples of the form B and A, and the samples drawn from the same domain respectively, uniform samples. So the new result states things over ring LW and ideal lattices. So one thing to notice from this definition is that here the lattices are basically ideals of a ring. Ring itself is an ideal, and ideals have these multiplicative and additive nature, both. So if we this is a big reduction from this SIDP to LW, but if we can talk about it in one slide. So the first sub problem is to reduce SIDP to DGS. I talked about DGS, define DGS. So DGS is an intermediate problem, and the second sub reduction is DGS to search version of LW. This is the actual result. And the third reduction is the search version LW to decision version of LW, and based on the decision version LW, we create the crypto system. So this is the set of reductions of the whole both of the results. First result is on Euclidean lattices, and the second result is on ideal lattices or ring LW. So through the analysis, we found out some of the areas of concern in the reductions in ring LW and ideal lattices. First of all is the ring restricted to cyclotomic ideal lattices. So the lattices are cyclotomic ideal lattices instead of Euclidean lattice. The approximation factor of the lattice problem or the SIDP problem. Another thing called tightness gap of the reduction. We define tightness gap and show what are the problems over there. And the quantum part, I'll not go into the quantum part a bit, but I will just tell one or two points to you. So in 1996, Atai and Doerr worked to show the provable security guarantee for the crypto system based on the worst case to average case reduction from lattice-based problem. And paraphrasing some of the remarks, support of worst case to average case assumption. So that is, worst case to average case reductions give the hard and fast guarantee that breaking a crypto system is at least as hard as breaking the hardest instance of some underlying problem. This gives a true lower bound of security and prevents unexpected weaknesses that have so often exposed schemes that lack this kind of security reduction. So just one line for this worst case to average case reduction is that when we build crypto system, we build crypto system based on problems which are hard on average case, because when you are making crypto system, we are choosing parameter from a distribution uniform. But if we consider any NP hard problem and we choose any instance uniformly, it is not guaranteed to get a hardest of instances. Whereas worst case in NP hard problem, the set of instances where the problem is actually hard or the hardest are a subset of instances. So from worst case to average case assumption, we try to see that we have proved, like the Atai work proved that the average case instances of some lattices sometimes it gets the worst case hardness. So this makes the crypto system at least as hard as breaking the worst case instance of the hard lattice problem. So that is the idea of the provable security they exploited, but in an asymptotic sense. So in the next section we'll see what are the things. So I said that first point is cyclotomic ideal lattices. So the worst case to average reduction is shown for general lattices, and SIVP is an APR problem in search version and both in approximation version for where the gamma is very small, the approximation factor is very small. But ideal lattices has much more structure. What are the structure and symmetry they are talking about? Because this ideal lattice comes from ideals and it has both multiplication and additive structures. And for implementation purpose, we are choosing cyclotomic ideal lattices. What are cyclotomic ideal lattices? So when we build number field, cyclotomic number field, we choose the irreducible polynomial as cyclotomic polynomial. The cyclotomic polynomials are of the form x to the power n plus 1, where n is the power of 2. So the two-dimensional cyclotomic ideal lattices, if you see the two-dimensional cyclotomic ideal lattices, they are basically tying the whole plane r to the r square by squares and equilateral triangle, something like this. So if we have this kind of lattices, then solving problems like BGT, CVP is very easy. We don't need much algorithm, like rigorous algorithm to prove or find out the shortest vector problem. Even for general lattices, for two-dimensional general lattices, this problem is easy. But the basis reduction by Gauss is not a trivial one, and it needs like the paper by Goldwasser and Michalcio, it has like 7 pages proof, only to prove that the algorithm is polynomial type. So if we consider cyclotomic ideal lattices and the equivalent lattices, there is a difference of hardness with respect to the lattice problems that you are considering. And this is not straightforward to see that if we change the lattice dimension from 2 to 4 to 8 to like 2 to the power 10 to the power 20, the difference in hardness changes. So that is not very clear. And next thing is that in cyclotomic ideal lattices, SIVP and SVP problems are basically the same. So if I have a solution for SVP, and we know that cyclotomic ideal lattices has n units, n roots of unity, we can multiply that sort vector with these roots, and we get n independent vectors, and which are the solution for SIVP gamma. So SVP and SIVP are both same in cyclotomic ideal lattices, which is not true for general lattices. SIVP at least as hard as SVP in general lattices, and to be precise, SIVP root n gamma reduced to SIVP gamma in general lattices with n dimension. This suggests that SIVP would be easier in cyclotomic ideal lattices than general lattices. And there are some preliminary attacks on ideal lattices due to Dan Bernstein and Tamina Lambe, and they call it asymptotic attacks. And this paper was published in 2013. So in last 1 decade, we have some few attacks, but not such a big scale attack to say that lattice-based cryptography or the cyclotomic ideal-based lattices are totally, we don't have that evidence. But still, there are a lot of time to explore whether those weaknesses can be exploited further. And so the main thing comes to the mind that why are we using cyclotomic ideal lattices instead of general lattices? The idea is to get efficiency. So in RLW, one sample is we can replace n LW samples, because in RLW the elements that we are multiplying, there are elements from polynomial ring. These are basically polynomials. So using one multiplication, we are getting these samples which can replace n samples. And also the multiplication can be done using NTT, which is a specific version of fast Fourier transformation. And this is possible. I cannot say that only possible because of the cyclotomic ideal lattices, But because of cyclotomic ideal lattices, we can use that fact and get a like the multiplication can be done in n log n time instead of n square. Yeah. So the next point is approximation factor of the problem SVP or SIP, because we know that SVP and SIP are both same in case of cyclotomic ideal lattices, and the SIP gamma. Gamma is the approximation factor. We calculate the gamma and we get that n to the power 7/4 and delta to the power minus half is a lower bound for gamma, and we are actually negating the logarithm terms. So to do the whole reduction, gamma needs to be at least this, and so initial result says that SVP gamma is unlikely to be NP hard for gamma greater than n, and it is due to gold washer and gold reefs, and SVP would fall under NP intersection co-Arthur margin Turing machine plus. So if we take an example, like the niece tells us that we need to have dimension 1024, that is MP over 10, and the delta is the advantage of the distinguisher. So the distinguisher advantage is we look for 16-bit 64-bit security or 128-bit security. In that case, delta would be for 128-bit security, delta would be 128, beta would be 128. But for our purpose, let's take beta equal to 45, and the gamma becomes greater than 50 or 40. The known SIVP gamma or SVP gamma takes time to the power n by k, and where gamma is to the power k. For n equal to 1024 and k equal to 40, the time required to solve SIVP gamma is 2 to the power 25. So this is not something satisfactory, because we are basing our hardness of security of our crypto system based on SIVP problem, which can be solved in to the power 25. But this algorithm is some heuristic algorithm, not the actual SIVP search version. So in practical, we want this value 2 to the power 25 to be above 2 to the power 128, and to do this, we need small gamma. If it is the gamma is small, the time would be more. But through our calculation, another thing came up is that Q, the modulus, should be around 2 to the power 35, but NIST prescribes that the Q should be around 2 to the power 40. So based on these calculations and the reductions, this doesn't go with the recommendations. But the thing is that when they proposed these reductions, they were actually not saying that SIVP is an NP hard problem that they are considering. That they said that SIVP is a hard problem, but from our calculation, the value of gamma is so big that we don't think that obviously it's not NP hard, and the main thing is that there's a gap that needs to be filled. And the third is tightness of the reduction. So tightness of the reduction is something that can be defined in many ways. Like we are reducing some problem from if the dimension changes from n to root n, that can be a tightness gap in the reduction. In our reduction, in this reduction, we define tightness as number of times we are using our oracle to solve the problem. So as per definition, suppose A is an algorithm that given access to an oracle O trying to solve the problem B in time t. Let's remove the success probability for the time being. Further, this O takes time t dash to solve P. Takes time O to suppose this O oracle takes time t dash. So the tightness gap would be t by t dash, and the reduction is considered tight if the tightness is one or small or else it's loose. So the reduction says that we are building crypto system based on LWE, not based on lattices directly. Through a reduction chain of reduction, we are getting the hardness of lattice problems. So if we had some system where we can directly build the lattice crypto system based on lattice parameters, then these things would be minimized. Is a general idea. What is the significance of tightness gap? So if the tightness gap between an exponentially hard problem and the problem of breaking the crypto system is polynomial, then for cryptographic values of parameters, we have a constant guarantee that the breaking the crypto system is infeasible. So informally, what we are saying that the tightness gap means the number of times the decision arbitrary oracle has been queried to solve SIP. How many times I am calling this arbitrary oracle to solve SIP. So suppose that the problem Q or the hard problem is SIP, and we are trying to solve this, and P is the breaking the crypto system, which is arbitrary. And for reasonable parameters, the best algorithm to solve Q takes time T and the reduction gap is G. Then we get a lower bound of T by G. Lower bound of what? Lower bound of the problem of P. So basically T is a hard lattice problem. So we can say that T is order of exponential, some 2 to the power n, and G is some polynomial gap, some Gn. So 2 to the power exponential by polynomial is an increasing function. So after certain values of n, obviously it will be exponential, but the minimum value of n for which this bound is exponential is something that we need to look. So we calculate the tightness gap from ideal SVP to ring LW, which is around Q n to the power 10 and delta to the power minus 10. And if we put these values, we get G, which is the tightness gap, is around 685. And we are like very optimistic that and we did not take this delta to the power minus 120. For 120 with security, we need to take delta 2 to the power minus 120. And we assume that the quantum algorithm for SIVP will not outperform the quantum the classical base known algorithm for SIVP. And if the base classical exact SIVP time takes 2 to the power n by 3, which is around 2 to the power 350 for n equal to 2024. And based on these calculation G, that lower bound comes as 2 to the power minus 335, which is a useless lower bound, because to the provable security, we need to have something from the whole reduction that says that the minimum time to attack the crypto system is around 2 to the power 128. And this minus 335 came with the optimistic parameters, not the actual parameters. So my point was like the whole reduction, everything that was promised to have provable security, but with the parameters that they are using, it is not giving as per what is prescribed. And the last point is the quantum reduction. So we're not an expert in quantum, but few of the points that I'd like to share that the quantum computer. So the assumption is the quantum computer can handle both nested sequence of algorithms as well as classical computers. So if I say that see that the algorithms in LTR paper, the whole reduction, there are 10 different algorithms, A0 to A7, D1 and D2, and A2 is the quantum part, which is used to solve the discrete Gaussian sampling problem. So input of the discrete Gaussian with the length say R, and the output of the discrete Gaussian, output of the quantum is the discrete Gaussian of length R by 2. And this is the algorithm. And in this quantum sample, they are using this CVP oracle. A CVP oracle is closest vector point. So problem, and this closest vector problem is solved by relational LW oracle. So what they do is that A2 creates a quantum circuit of and the quantum circuit is roughly 2 to the power 3n square dimension Hilbert space for n to the power n equal to 2 to the power 10. This equals about 750 times as many logical qubits as Shor's algorithm to break 2048 bit RSA modules. So the quantum circuit requirement is huge, and if one tries to improve the security, by increasing n. So in tightness gap, we saw that the tightness gap is huge. One can increase n to reduce the tightness gap, and then his value 750, it would be like in millions. And the algorithm has said that the linear combination of roughly 2 or 3 square terms is involving two entangled resistors, and A2 needs to erase one of the resistors when uncomputing, and the process vector in each sum. And so the quantum computation must incorporate everything from A2 to D2. So we think that's kind of infeasible with the current state of art. And things like quantum decoherence and then result inability to store data for a significant time would be a bottleneck for this reduction to process. But some of the points in the quantum part is somewhat speculative because based on the we're not expert on this. And in conclusion, so the practical crypto system is not based on RLW directly, but based on module lattices. So module lattices is basically a generation of ring ideal lattices. So n, the dimension is n cross d, where n is the dimension of the number field and d is the module dimension, t. And the module lattice is kind of a hybrid between these two lattices, general lattices and the ideal lattices. From general lattices, it tries to harness the hardness, and from ideal lattices, it tries to take efficiency. But the problem is that in both the schemes, MLKM and MLDSA, N is 256 and D is 234. So the module lattices are basically going for ideal lattices more than general lattices. So all our points that we made are completely applies on these. And in conclusion, I should say that our work doesn't imply that the lattice-based crypto is insecure. It may be secure because we are using it and we are constantly doing research to find whether there is some security loopholes. But the point that I'm trying to make is that the provable security, which is the base of this, base of the lattice-based cryptography, is not at least at its perfect state. So we need to do more research and find out all those gaps and come up with better results. So that's it.
There any questions?
So on slide 30, you talked about this estimate you did of what the runtime success probability would be for this optimistic parameter set.
Yes.
Did you try to find a parameter set that actually does achieve meaningful security? And if so,
Yeah,
how
this
bad is
is
that?
way beyond is at least over 2 to the power 20 or 25. So
For what?
for n dimension equal to 2 to the power 25. So it doesn't make any sense. So we're working with 256 into 2, 3, and 4. That means 512, 768, and 1024. That's our operator. We have three different security ranges. So it doesn't make any sense.
So you need so you're saying you need n equals 2 to the 25 or bigger?
Yeah. So at least, and another thing is that the tightness gap analysis is not based on the raw reduction that they produce. We try to optimize the 9 reductions as per our understanding, and we actually optimize few of them. So I could remember that there is somewhere we use Renyi divergence, and there it was introducing n to the power 3 kind of tightness gap, and we made it up to root n. And somewhere there was somewhere it was using n square of n to the power 4 by 3, and we can use the constant number of samples, we can achieve that. So we try to optimize, but the results from the G Q equal to n to the power 20, this is the optimized result. This is not based on the raw results by Regev and Pickens and Lewis. Yeah.
Any other question? Basically, I had a feeling you say that these they came up with 3 by 4 algorithm, three
Yeah,
or ladies and one hash base.
Hash list, yeah.
You know the reason why ladies is so much better than isogeny. Isogeny was like several hatch some years ago. So is it like just isogeny is not ready yet? Or is
So
it
isogeny is that the thing is that in 2002, the isogeny hard problem is there, but for efficient implementation, what they did, they choose a like as per my understanding, I actually talked to David once. So David told me that they choose a sub problem, and back in 2020, it was proved that sub problem can be broken. So that is the state of isogeny. And like RLW is basically chosen over normal LW because of the efficiency. So public key cryptography is not that efficient. Once this is efficient, people will use it. So it has economic sense to it.
So I have a question. I I think a lot of people in cryptography, like me, would think that this kind of reduction would be a nice thing to have, and if it kind of falls through, it's not the worst thing, and maybe the cryptography is still secure. It's kind of a subjective question. Would you trust right now the module like MLCam and Kyber to secure your data?
Yeah, the thing is that there was a discussion which Dan Monstein made. So he's like he makes many comments. So he was trying to push NTRU. So based on that, NTRU was also a lattice-based system, and this is module lattice-based system. The only thing that it doesn't have any security proof. So his point was that NTRU is faster. It doesn't have any security flaw that we know of, but it has like module LW has security proof which is not up to the mark. Asymptotically is very good, but practical from practical aspects, it's not up to the mark. So why not use NTRU instead of module lattices where we get more efficiency, but we don't have like his point was that having flawed provable security is equivalent to having none. So until and unless we have something, why not use? But if you ask me, as long as like yeah, we can use module, but if like it's not me to take this decision, but in the big corporation who are actually doing these implementations, if something happens and it's a huge financial impact that we're going to see. So next best solution is to go for hybrid. So use diffie-Hellman type and use, let's say, module chem in hybrid mode. It will take some more time, but at least it is secure. The first focus should be on security than efficiency. That's my point. Oh.
If no more questions, then let's thank Subhadip again.